Hello everyone, I'm Neil Zhao from University of Illinois. Today I'm going to talk about my work, Speculation Invariance, Faster Self-Execution Through Program Analysis. Modern microprocessors are threatened by speculative execution side-channel attacks. Attackers use transient instructions, which are instructions that bound to squash to leak secrets. Here's an example of how it works. Attacker has control over variable x, and attacker wants to perform an out-of-bound access. Attacker will set x to a value larger than array1 size and mistrain the branch predictor, which will cause the processor to mispredict. So the processor will execute these two transient instructions and leak the secret. To defend against such attacks, most existing hardware defense apply special hardware mechanism that protects instructions while they are speculative. When the instruction reaches visibility point, the protection is lifted. Here's the definition of VP. Is the point when the instruction can execute safely without protection. It depends on the threat model. In Spectre, we are concerned about squash caused by mispredictions, so an instruction does not reach VP until all older branches are resolved. For example, the protection on node 1 will not be lifted until the branch resolves. In comprehensive model, we consider all types of squashes. We require the instruction cannot be squashed anymore to reach VP. For example, Node 0 can cause squash due to memory consistency violation or exceptions. Therefore, the protection on Node 1 will not be lifted until Node 0 cannot cause squashes anymore. Before diving into more details, I want to introduce two more concepts. The first one is squash instruction. It's an instruction that can cause squashes that may lead to security violations. Just like VP, it is defined by the threat model. The second definition is transmitter instruction. It's an instruction whose execution can create operand-dependent microarchitectural resource usage that reveals a secret. In the example above, the branch is the squash instruction, since it can cause squash by mispredicting. And the load X is the transmitter, since it can leave footprint in the memory hierarchy. Here is what the ROB looks like. It has a transmitter load shadowed by an unresolved branch. Take defense scheme delay on miss, for example. It will only allow the load to access L1, and if it misses in L1, it delays the load until the VP. However, hardware can be overprotecting sometimes. For example, if load X is neither data nor control dependent on the branch, load X will always read from the same value of X and commit. Therefore, we do not need to protect load X. However, the ROB looks quite similar to what we had before. We still have a transmitter load under the shadow of an unresolved branch. So, the DOM will still delay the load if it misses in L1, which can lead to performance loss. The fundamental reason is that hardware only has the view of dynamic execution path. It has no knowledge of the both direction of the branch. Here, we wish that load X can execute before turning non-speculative. To do this, it requires software support so that hardware can identify this case. The high-level insight of our solution is called speculation invariance. The intuition is that a speculative instruction can become speculation invariant at some point before turning non-speculative. In this example, the branch controls whether the load X executes or not. Because of this control dependence, load X is not speculation invariant. In the second example, the branch controls where the load reads from. Because of this data dependence, it is not a speculation invariant. In the third example, the transmitter has neither data nor control dependence on the branch. Because of that, load X is speculation invariant. The concept can also be applied to the case where loads are considered as squashing instructions due to exceptions and memory consistency violations. In the first example, the load X has control dependence on load Y, so load X is not speculation invariant. In the second example, the load X has no dependence on load Y. Therefore, load X is speculation invariant. The contribution of our work is InvarSpec, a software-hardware framework that identifies when a speculative instruction becomes speculation invariant and allows the execution of the speculative instruction without protection. InvarSpec has two core components: static analysis path of a program, which takes a program as input and generates the software hints called SafeSet for the program. It also has core microarchitecture added on top of existing secure schemes. It will take the software hints input and improve the performance. Our evaluation shows that InvarSpec can substantially reduce the execution overhead of existing hardware defense schemes. Now I'm presenting the formal definition of speculation invariance. A speculative instruction I becomes speculation invariant when whether I will execute and the value of I's source operands do not depend on speculative state. For the two examples on the right side, load X and the value of X do not depend on the outcome of the branch and load Y, which are speculative state. Therefore, load X is speculation invariant. We say that instruction I reaches its execution safe point when its speculation invariant and its source operands are ready. Our proposal is that we lift the protection mechanism as soon as a speculative instruction reaches its ESP and execute it without protection. The intuition is that as soon as the instruction reaches ESP, it is guaranteed to eventually commit using the exact same operands despite any future swatches. To see what we will gain by doing this, I'm showing you the timeline of transmitter. First, the transmitter is ready to be speculatively executed. This is when a traditional hardware mitigation will engage its protection. Then the transmitter reaches its ESP. After that, the transmitter reaches its VP, and this is when a hardware scheme without InvarSpec will lift the protection. After that, the transmitter will execute and eventually retires. By adding InvarSpec, we can lift the protection as soon as the transmitter reaches its ESP. Thus, it can execute earlier and improve performance. Because hardware cannot detect speculation invariant effectively by itself, we are providing software hints to the hardware. Such hints are called self-set. Self-set for an instruction I is a set of older squashing instructions that cannot prevent I from becoming speculation invariant. For example, here the branch does not control whether the load executes and the value of X, so the branch is in the SS of load X. And the same thing applies to the load Y here. To show you why self-set is helpful, let's think about when is the hardware sure that instruction I has become speculation invariant. First, if hardware does not know I's SS, it needs to be conservative. It will require all of its older squashing instructions have produced their final results. On the other hand, if the hardware knows I's SS, we can relax the condition a little bit and only require those older instructions that are not in the SS I have produced their final results. Because now a transmitter will wait for fewer squashing instructions to produce final results, it can be executed earlier and improve performance. Before diving into how to generate SS, I want to take a small detour to talk about the threat model of InvarSpec. Because our goal here is to improve performance of existing hardware defense schemes without compromising their security. InvarSpec inherits the transmitters and the threat model from the hardware defense scheme that it augments. And we rule out attacks based on the exact timing of when speculative instructions execute. The reason is that the underlying hardware schemes that InvarSpec augments do not consider them either. And in this paper, we will focus on a threat model where we consider squashing instructions are branches and loads, transmitters are loads. InvarSpec framework has two main parts. On the software side, it has an analysis path that generates SS for the instruction. It has a baseline analysis which populates SS with instructions that are safe for all the execution paths. It also has an enhanced algorithm which will place some instructions that are not safe for some execution path into SS. On the hardware side, it has microarchitecture in the processor core which brings SS of the instruction being executed to the pipeline and computes when the instruction becomes speculation invariant and can execute. Let's first talk about InvarSpec baseline analysis. It starts with building instruction dependency graph. The instruction dependence graph of instruction I is a graph that contains all instructions within the same function that may affect whether I executes or the value of I's source operands. For the example code snippet here, let me show you how to build the IDG of load X. First, because load X has data dependence on the load Y, we will add an edge from load X to load Y and label it with data dependence. Then, we find that load Y has control dependence on the branch, so we'll also add an edge from load Y to the branch and label it as control dependence. Note that all the descendants of loadx in the IDG are the instructions that may affect whether loadx execute or the value of x. So, we will subtract the descendants from all the older squashing instructions in the function, and it can generate SS of loadx, which only contains loadc in this case. We also have an enhanced algorithm based on an insight that some dependencies only exist on certain execution paths to I, and we will remove some edges from the IDGI and place more squashing instructions in SSI, which can result in better performance while still being safe. Please refer to our paper for more details. Next, I'm going to talk about microarchitecture of InvarSpec. To store SS, we will allocate an additional SS page for each code page with a fixed virtual address offset. So, for instruction like load0 here, which has an SS, we can easily access it by adding the fixed offset to the PC of load0. To keep the recently used SS close to the core, we will have a small SS cache. When the instruction is decoded, the SS cache is checked. If it hits, it provides the SS, and if it misses, it will request it when it's safe to avoid creating new side channels. To compute speculation invariance, we have a small in-flight buffer near the ROB. IFB records all the in-flight transmitters and squash instructions. Each IFB entry looks like this. It records the PC of the instruction. It has a bit mask that contains SS information. Then we have a final bit, which tells whether the instruction has produced final results. Finally, we have an SI bit, which tells whether the instruction is speculation invariant or not. During execution, for an incoming transmitter I, it will grab SS from the SS cache and compare it against all the existing older IFB entries. And if there's a match in the PC, we mark it as 1, otherwise we mark it as 0. Then we will aggregate the comparison result to generate the SS bit mask for transmitter I and insert it to the IFB. The hardware will update the SI bit of transmitter I periodically using the following logic. It first grabs the bit mask of the transmitter I. Then, for each bit, it will do the bit OR operation with the final bit of its corresponding IFB entry. Then, use the AND operation to aggregate the results, which toggles the SI bit. The reason why it's correct is because it infers that all the older IFB entry is to be either safe or have produced its final result. To evaluate the effectiveness of InvarSpec, we measured the average execution overhead of InvarSpec over conventional unsafe core on Spec 2017 with Gen 5. We evaluated 3 schemes in total. The first one is fence, which plays fences before speculative loads. The second one is delay on miss. It allows speculative loads to access only L1, and it stalls if it misses on L1. The last one is InvarSpec. It invisibly issues speculative loads and follows up with a second access. For each hardware scheme, we evaluated with 3 configurations. The first one is vanilla, which is the defense scheme without InvarSpec. Then we have SS. It's the defense scheme with InvarSpec baseline analysis. Finally, we have SS++. It's the defense scheme with InvarSpec enhanced analysis. And here are the results. Let's go through them from left to right. First, let's consider fence, which has a very high overhead around 200% without InvarSpec. Applying InvarSpec baseline, we can achieve some moderate speedup, and if we further apply InvarSpec enhanced, we can bring the overhead down to 108%. Next, delay on miss. It has a moderate overhead around 40%. This time, applying InvarSpec baseline does not help much. But if we apply InvarSpec enhanced, we can bring the overhead down to 24%. Last one is InvarSpec. Its execution overhead is around 15%, and applying InvarSpec enhanced can bring it down to 11%. Based on the evaluation results, we can say that InvarSpec delivers substantial reductions in the execution overhead of defense schemes. The takeaway of this talk is that InvarSpec is a defense scheme against the speculative execution attacks that combines cooperative compiler and hardware mechanisms. InvarSpec can augment many existing hardware-only defense schemes, and it can substantially reduce the overhead of defense schemes. For more details, please check out our paper at the following link.